Okay, so the first presenter today is the Konstantinos Rogdakis from the Hellenic Mediterranean University that will present topic related to the emerging PV technologies. So Kostas, please share your presentation. You can start.
Thank you very much for the introduction. So let me share my screen. Please tell me if you can see the slides in full mode.
It's okay.
Okay, so thank you very much. I slightly changed the title of the talk. Since at the beginning I thought I should focus on energy because the pillar in the webinars that we are going to present in this session is mainly on energy. So the initial talk was about perovskite modules and panels evaluated outdoors. However, I also checked the other talks that are also focusing also on electronics. So I thought, why not to present also our results on neuromorphics. And the common point here is that we developing perovskite-based solar cells and modules using also 2D materials. So we include various layered materials like graphene and other 2D materials in a typical perovskite solar cell and module. So this is the one direction. But at the same time, we are using more or less the same structures here in order to demonstrate neuromorphic computation functions. So in this way, I will dedicate one part of the talk at the end on neuromorphics, but using the same platform, the same material platform that can more or less at the same time exhibit, of course, solar energy harvesting as a solar cell, as a solar module, but at the same time, we can tune the device in a second mode and operate as resistive switching memory as a neuromorphic, let's say, computation element. So this is somehow also related to energy because everybody now knows about all this big data, machine learning activities in the world. So everyone knows about GPT and other LLMs. So this kind of devices require a huge amount of power for their operation. So we think that neuromorphics, that are devices that mimic the operation of the brain, could be a solution to the problem of the, let's say, big data analysis. So these devices can operate at very low power consumption compared to the standard GPUs that now the community uses for the LLMs, for GPT, for example. So this is in the same, let's say, direction. We are going to develop solar cells using perovskites and 2D materials, but at the same time, we can develop resistive memories, so neuromorphic computation devices to perform low power consumption computation. Okay, so this is the general overview. As you introduced, I'm assistant professor in Hellenic Mediterranean University, and one activity is the photovoltaics, and the other is the electronics. So very briefly, this is the outline of the talk today. So the first part is how we integrate 2D materials like graphene in typical perovskite solar cell and solar module devices. So this is our group actually participated in graphene flagship. Here is a big European project the last 10 years or so on developing perovskite cells and modules and even panels at the very end, and using 2D materials to improve the performance of this kind of solar cells in terms of power conversion efficiency and stability, lifetime stability. So I will try to show you some results from our group on perovskite solar cells and modules using 2D materials. And as a highlight of graphene flagship, so our group was the leader for Rogdakis 11 on energy generation. So together with colleagues from Graphene Flagship, we demonstrated the first solar farm in the world by integrating 9 panels. So for the first time, we have the production of panels of 1 square meter each, PV panels based on perovskite technology and integrating graphene and other PV materials. So all this processing here, the manufacturing is based on solutions. So in principle, can be a printable technology. So we can print this kind of panels. And when we say print, this indicates that the manufacturing cost could be lower than silicon technology. And of course, the impact on the environment is much less. The highest temperature here is around 150 degrees, while for silicon, we have to go up to thousands of degrees to produce the wafers and all this stuff. So this technology could be, let's say, more sustainable compared to silicon and other inorganic semiconductor technologies. So it can have a lower impact on the environment. And in the second part, I will try to briefly overview our activities on neuromorphic computation, mainly for the Internet of Things edge computation. And as I told you, this is related to the energy sector because this technology could be a solution to the power consumption problem for the big data and the machine learning activities nowadays in the community. So what we have demonstrated here is actually memory strip solar cells, so devices that in principle can harvest solar energy like every solar cell is doing, but at the same time we can tune the device to a second mode of operation, and we can demonstrate neuromorphic computation, or what we call it processing in memory computation. So this architecture goes beyond von Neumann architecture, and this is the reason why the power for implementing this computation is much less compared to conventional CMOS technologies to standard, let's say, computers. Okay, so we are within the infra chip, so usually also I present the infra chip, but also our colleagues before me already described the infra chip. So a few words about our lab, headed by Professor Manuel Kimakis. So our lab is placed here in Crete. Crete is an island at the south part of Greece. In this map, you can see the global irradiation, let's say how many kilowatt hours per square meter across Europe we can have. And you can see that Crete is an ideal place, and even Greece in general, but even Crete is the best place, one of the best places to develop PV technologies. So this is the overview of our lab. As I told you, we are more or less around 20 researchers in the lab. 4 main activities. The first one is to develop, we have a group to develop graphene and related 2D layer materials, inks and paints. What I will show you today is everything is printable based on solutions. So we develop inks using 2D materials, and then we integrate them in either organic photovoltaics or perovskite-based photovoltaics or solar cells at small scale. And also we have the equipment that we offer also through InfraChip for the large-scale fabrication of modules and devices using, let's say, a mini roll-to-roll system and other techniques for large-scale fabrication. And one focus is also the indoor and outdoor characterization of the devices that I will focus today, especially outdoor characterization of emerging technologies like perovskite is very important to understand the potential of this technology at some point to be commercial and complement the commercial technologies using silicon or other inorganic semiconductors. And the fourth direction is going beyond PVs and address flexible electronics. So we have activities on developing printable transistors, sensors, and memristors that I will focus at the end of the talk about these memristor solar cells that can implement neuromorphic computation. Okay, so this some of our let's say facilities. As I told you, we cover from the material formulation, characterization, to lab scale fabrication and up to upscale manufacturing processes. Either, let's say, targeting PVs, photovoltaics, or other flexible electronic devices. Okay, we have some pilot lines, some glove boxes. Most of the materials that I will show you today are sensitive to atmospheric conditions. That's why we have these glove boxes. We have control conditions, almost zero oxygen and humidity that allow us to fabricate high quality devices, a series of characterization techniques for both material characterization, but also device performance evaluation, indoor, and also these are some examples of large scale fabrication, machines that we have, screen printer, mini rotor roll in our lab. And we have this open air lab dedicated to evaluate the performance of PV technologies outdoors. These images from the perovskite panels that I told you before that are installed in our lab. So before going to this highlight of graphene flagship, let me say a few words about what we are doing the last 10 years. So this is a typical solar cell structure. Don't know the audience if they have the experience about solar cells, but the typical way it works, you have an active layer. In our case is, let's say, perovskite or other organic material. Perovskite is very, very fascinating material. It's a hybrid structure, so you have also inorganic and organic elements inside the active layer. So this makes it very interesting material with emerging properties. So actually here you send some light through some transparent conductors, and then you create some excitons, electron hole and holes pairs, and then you extract electrons and holes separately. And in this way, you convert the light to, let's say, electricity if you close the circuit. So the last, let's say, 10 years in graphene flagship and not more and beyond, we were trying to improve the performance of the devices, or this kind of devices, by integrating various 2D materials, different positions of the structure. So either at the interface between, let's say, the whole transport layer and the perovskite, or between the electron transport layer and the perovskite, or even by doping some layers here with 2D materials and other nanoscale materials. So what was demonstrated was that using 2D materials, we can improve through interfacial engineering approach, let's say, we can improve both the efficiency, the power conversion efficiency, and also the lifetime stability. That is a big problem for organic PVs and perovskite PVs. While in principle, the manufacturing cost can go down using printing technologies. So now, why we need, let's say, novel energy conversion technologies like perovskites, both at small and large scale. So this is a report published by the International Renewable Energy Agency, IRENA. So the last 20 years. So if you check here and compare what was happening 20 years ago, 25 years ago, and what is happening right now, we can see that Europe, let's say, has achieved the reduction of CO2 emissions. That is very important. And this was done by developing more wind capacity, PV technologies that allow us to increase the global renewable share in electricity. And at the same time, this development led to a decrease in the cost of electricity production by 20x based on PVs, for example. And also at the same time, of course, it's important to develop energy storage units for batteries, in order to be able to store the electricity produced by renewables and use it when this is required. So while this is a good progress, a greater acceleration is needed. So then we should work more for renewable technologies, electrification, and energy efficiency improvement. So this is, let's say, large-scale point of view, but at the same time, everyone now has many smart devices everywhere. For example, in our cars or in our houses, we have smart, let's say, TVs, iPads, smartphones. Everything is smart, so everything is connected to the internet. So this is what we call Internet of Things. All the devices are connected to the internet. And however, if each of these devices consume a small amount of energy, but if we take in account that we have billions of devices, so all this kind of technology here requires a lot of energy for the operation. So powering billions of nodes of this kind of elements of the IoT network is very important issue that we have to address. One option to overcome this is to integrate smart energy harvesters to this kind of devices in order to make them self-powered and then address this power consumption issue, and at the same time avoid to use batteries or wires for the connection of these devices to the grid. So this is, let's say, the roadmap of our lab. Our focus is to use 2D materials to develop, as I told you, energy harvesters, not only photovoltaics. For example, here you can see a solar farm that is already a reality in our lab. We have developed perovskite panels using 2D materials also in order to produce quite big quantity of energy. But at the same time, we can use 2D materials to develop emerging harvesters like piezoelectric generators, devices that can convert humidity to electricity, or even on the left, you can see some ways to convert water-based energy to electricity, like the waving potential here in this case, for example, or harvest the salinity gradient between a river and the seawater, for example. If you can place, it's already demonstrated, you can place 2D material-based materials at the interface between a river and seawater, for example. This salinity gradient can be converted to electricity. So there are very interesting ways to harvest ambient energy that is available everywhere without affecting negatively the environment. So all these technologies are green technologies. So in this paper also we summarize all the progress using 2D materials, but also we propose some ways to improve the efficiency of these kind of devices. For example, we can integrate together different types of harvesters. So like here it's a PV panel array, some wind generators, and also some turboelectric generators, this kind of elements here inside the water. And all this movement in the water of these elements can produce electricity in a complementary way. Okay, so let's move to the perovskites technology using 2D materials. As I told you, the last 10 years, we worked on different 2D materials like bismuth telluride, for example, here. So we developed bismuth telluride nanosheets and we prepare some inks, and we use this kind of inks in order to improve the performance of the solar cell. For example, we test them as a dopant inside this PCBM layer, and also as an interlayer between the PCBM and the perovskite layer. So in both ways, we demonstrated improvement in the PC, in the power conversion efficiency, but also an extended lifetime stability while testing the devices under ISO's protocols. Here, for example, we put the sample for at least 1,000 hours inside a chamber at elevated temperature, 65 degrees. And here is a series of papers that we published in the last few years. Another approach was to use tantalum disulfide nanosheets, as shown here. Again, we develop a layer between the silver contact and the PCBM layer, and in this kind of configuration, we demonstrated a much better stability, lifetime stability, under various conditions using this interlayer formed by the 2D materials. Here, another approach was to use bismuth telluride iodine as a dopant inside the perovskite layer. So we demonstrated that we can find the best concentration of these nanosheets-based inks in order to improve the power conversion efficiency. Here, another direction was to find a way to replace, to improve the quality of the interface of the perovskite with some organic here ETL, Spyro layer. We have tested various 2D caps, 2D passivation layers, and we observed improved performance using this Obr material as a capping layer of our perovskite devices. And in this study on the right, we replaced the noble metal contacts that are usually gold or silver with carbon-based material, and we demonstrated even better performance compared to noble metals. So replacing noble metal electrodes is a very important direction because we can have a fully recyclable device, and of course, the manufacturing cost goes down. Okay, so this is a recent also overview about indoor perovskite photovoltaics for the IoT development. Okay, so this is, as I mentioned at the beginning, one of the highlights of Graphene Flagship, a collaboration between, of course, our group, Aldo Di Carlo Group in Italy, Francesco Bonacoso, B-Dimensional Company, and other colleagues across Graphene Flagship Consortium. So all this huge effort led to the first demonstration of 9 panels. So each panel here is based on perovskite modules, while integrating 2D materials at various positions, and designing and setting up a standalone system, solar farm, an autonomous solar farm structure. So we install the system, and we're still investigating the performance of the devices even after 3 years or so since the first day. So this paper was published in Nature Energy on the cover. It was let's say a real breakthrough. Let me say a few words about the activities. So as I told you, we started from the materials development. So our team and colleagues from other, let's say, partners, we formulated various 2D material-based inks. Then we used them at various positions, and we fabricated many modules. For example, each panel, you can see here, has at least 40 modules. Each panel has 40 modules. We have 9 panels, so we speak about 360 modules. Each module has a size of 10 by 10, so it's quite big. And each module contains, if I remember well, 8 solar cells. So we speak about, or 11. we speak about more than 3,250 solar cells using this kind of technology. So it was a huge effort, mainly by Torber Gata, so Professor De Carlo group that fabricated the majority of the solar cells. The company BDMS provided some encapsulants and for the encapsulation of the panels. Great Cell is a company in Italy that implemented the encapsulation and the lamination of the modules. And our lab in HMU designed and integrate all the panels in a solar farm structure that I will show you later. So a few words about the materials included. This is a typical structure for the perovskite solar cells and modules. So we integrated the functionalized MOS2 nanosheets between the PTAA and the perovskite, while we use graphene inks to dope the mesoporous titanium oxide layer here and the compact one. So as I told you, each module, it's 11 by 11 centimeter, consists of 9 in series connected solar cells. All this technology is in principle printable technology. And at the beginning, for each cells and modules, we implemented the ISO's test at 85 degrees and we passed the required tests. So then we integrate many cells, as I told you, 11 cells per module, and we fabricated 360 modules. This is the average PCE, power conversion efficiency per module. The average value was around that time 12.5%, with somehow a distribution of the values around this 12% mean value. Of course, this is not like a conventional technology like silicon. So we have a distribution that is expected for, let's say, a low to RL technology. Also, the hysteresis was not so bad. Then with our colleagues, we fabricated, we implemented the lamination. They used EVA as a material, and the goal was to use the lamination temperature as low as possible. So the maximum was around 85 degrees, although this low temperature at the end had a negative impact on the final lifetime stability of the panels that I will show you later. So we performed the lamination and then fabricate the panels. As I told you, we have 9 panels with an average PCE of 9%. This is the distribution of the output power per panel was around 30 watts, the average value. Here in HMU, we developed the solar farm, as I told you, all the electronics, all the inverters, integration with the batteries also. All the energy harvested from the panels is stored in these batteries, and then we use through an inverter this energy to supply power in our loads in our lab. We develop various MPPT, maximum power point track algorithms, all the electronics, all the interface for the monitoring of the output power, the energy produced from the panels, and also what energy is consumed by the loads of our lab. Very briefly, so this is the picture from our lab outdoors. These are the panels using perovskite technology, 2D materials, and we benchmark the performance of the devices against conventional technologies, commercial one. For example, here it's silicon, polycrystalline silicon. Here it's cadmium telluride, monocrystalline silicon. This is bifacial silicon PVs, again commercial. This panel is based on 6. We have a weather station integrated in the park. We can record all the conditions of the environmental conditions in the park and evaluate the performance of the technologies, the PV technologies, under different, of course, conditions, environmental conditions. Okay, so here are some. This is a full IV curve current voltage curve of the park, of the 9 connected panels. As I told you, we developed various MPPT algorithms and also a dedicated hardware here in order to be able to measure this new technology. It's a new hardware and a new MPPT algorithms developed by our group. Okay, so some details, but we can understand all the power electronics required to develop this system. Because we should measure at the same time very high current. Here it's 7 amperes, for example, and very high voltages, 70 volts. So it's for this we had to design a new hardware to be able to measure these properties. Okay, so these are typical measurements throughout through the course of the day of the park and the panels. We also measured hysteresis between morning and afternoon. So usually during the morning we have better performance compared to the afternoon performance. Another highlight was to extract the thermal coefficient for the current and the voltage from these curves. It was very important to identify that this perovskite technology has a very low negative but very low VOC. This is the open circuit voltage thermal coefficient that is very low. It's lower than the silicon. That indicates that this technology is affected less at high temperatures compared to silicon. So for some applications, it's better than better than silicon. Okay, and this is the main stability diagram of the paper. So for the first 9 months, this is the output power of the farm for a period of 9 months. We recorded the outdoors for a T80, so the performance dropped at 80% of the initial after 5,800 hours or so. So this is 8 months. So it was a quite good performance at that time. And but after this period, we recorded some visual effects, degradation effects in our panels. You can see these regions here that are reddish, that correspond to some degradation effects, either coming from moisture or humidity insertion in the panels. And the main problem was the lamination failure around the panels that allowed the penetration of humidity and oxygen in the panels, in the modules, and then in the cells, destroying some of the cells and the modules. At the same time, also we performed some LCA analysis, life cycle assessment of the technology, and we identified that bottlenecks are the gold evaporation that is still present on the panels. We have to replace gold with even probably with carbon-based material in order to make more sustainable technology. And also this drying and laser process here for the scrying of the panels is also a negative part in the LCA analysis. Okay, so to sum up, we demonstrated the first park in the world using a perovskite technology that is printable and also integrating into the materials. For the first 8-9 months, we have a very good stability of the technology, but afterwards we notice a lamination failure of the panels that started the degradation of the performance. LCA also indicated that we have to replace gold with some other more sustainable materials like carbon-based or graphene-based electrodes. And we're still working on this technology. So then, with a few minutes that I have, maybe I can go very fast. As I told you, with the same materials platform, perovskites and 2D materials, we can also develop neuromorphic devices. So in this session, I would like to show you our, let's say, goal. Our goal is shown here in this graph. Actually, is to develop a printable, flexible computation engine using perovskite again devices. Each red element here is a perovskite layer And in this crossbar structure, so we have a crossbar array of multiple nodes, of multiple devices. Each node here is a small memoristic solar cell. So this element can harvest energy, it's a solar cell, but at the same time, if we need, we can use it as a memoristic element. So we can do memoristic computation and neuromorphic computation using the same element. So we can have a self-powered computation engine using this material stack. So the last few years, we have developed this kind of concept, and also we integrated 2D perovskites and other 2D materials in the stack in order to improve the performance of the memoristic devices. Of course, these devices are perovskite-based. We can control the properties of the device, the resistance, for example, by light illumination, since it is a solar cell. So we speak about optoelectronic memristors here. So why neuromorphics? As I told you, if we follow the conventional, let's say, CMOS technology, what now the community is doing, we have some issues. We have to overcome the Moore's law, cannot scale down anymore. We should also overcome the heat goal and also the memory goal. So this is very important. Memory goal means that we have to transfer data from a memory element to a CPU, to a processor, and back and forth. And all this transferring of data consumes a lot of power. So this is why all these GPUs for LLMs, GPT, consumes huge amount of energy. So it's not sustainable technology. So we should find a ways to overcome this by developing another technology, what we call here neuromorphics or in-memory computation. And this path here can overcome the hurdles and allow us to achieve a big data, let's say, processing with not so much power consumption. Okay, about now optoelectronics, of course, it would be nice to have control of the resistive memory devices by light. Can give us an extra degree of freedom to tune the resistance of the devices, the memory devices by light. So how all this work? It was proposed initially by a group of Professor Lira from ICNU. So they developed a solar cell. That time it was an organic solar cell, and they used a ferroelectric layer as a whole transport layer, and they tried. Ferroelectric means it's a material that can be polarized by applying an electric field, and they show that they can tune the resistance of the device by polarizing or not this layer, and also, of course, they can tune the resistance by turning on light illumination because it's a solar cell. However, in their device concept, this ferroelectric layer required a very high temperature to develop it, more than 500 degrees. And also, they need to apply more than 10 volts to switch the polarization of the film, more than 10 volts. So both these make incompatible the device with low temperature manufacturing, cannot be, let's say, printed, cannot be on flexible devices, and also requires a high power for its operation. Okay, so this is some for the neuromorphics. Maybe I can skip all this. I don't have a lot of time, but just to go directly to the results. Here is some introduction about why we need the neuromorphics. As I told you, the main advantage is the low power consumption. Typical IV curve is like that. Actually, when you start from, let's say, 0 voltage, you start from a high resistance state, what HRS is meaning, it's high resistance state. And when you cross a threshold voltage here, you jump to a low resistance state. So then the device, if you go back, remains to low resistance state until you go to a negative polarity. And then if you exceed this threshold, the device will go back to high resistance. So this loop is a typical switching loop, and a memoristic device has two states, high resistance and low resistance. So you can use it as a memory, but also you can do computation using this kind of memoristic devices. Okay, so very briefly, there are different types. Let me go directly to our results because a few words about the mechanism. Probably there's a lot of discussion in the literature. What is the physical mechanism about this switching from a high resistance to a low resistance state? You can see here this graph. So the main mechanism proposed by the community is that is by applying some electric field. Actually, you induce a migration of some ions in the system that create some vacancies, and these vacancies that are left behind are conductive. So you form something like a conductive panel, a conductive path. What we call this? We call this as a filament. So this filament, this conductive path, is actually behind the low resistance state. And when you reverse the polarity of the field, electric field, you suppress this filament, so you end up to a high resistance state. So roughly, this is the mechanism. In various systems, either perovskites or oxide-based membristors. Let me go here. So what we have presented the last few years with our students and our team here. As I told you, we started from a standard solar cell structure that you can see on the left. This device can, of course, perform as a solar cell, but when we apply specific electrical bias, we can reset the system as a membristic memory element. So here from this IV, you can see very clearly two states. This is the low resistance state, and this is the high resistance state. So our devices can indeed perform as a membristor with two states, low and high resistance state, with a very good ratio, 10 to the 5. This is the difference between the low and the high resistance state. It's 10 to the 5. And we demonstrated typical protocols for membristors. It's the endurance characteristics of the device. What we call here endurance is we send electrical pulses and switch the device from a high resistance to low resistance, high, low, many times. And this is indicated by the cycling number. So we repeated this cycling from high to low 3,000 times with no degradation evident in our measurements. Another typical measurement is the retention characteristics. So here you set the same to the high resistance state, for example, and you monitor the resistance state on time until you see some degradation. High resistance state is very stable. The problem comes in the low resistance state that after a few thousand of seconds, the device jumps to high resistance state. So now we have some ways to improve the retention characteristics of the devices, like the plot on the right. Then we can, very briefly, we can tune the resistance state by light illumination. In this graph, you can see by increasing light illumination, we can increase the resistance from low values to high values almost in an analog fashion. So we can have a linear control of the resistance state by changing light illumination. So we demonstrated optoelectronic membristor that is tunable, of course, by electrical pulses, but also by light pulses. Okay, and then we demonstrated many synaptic protocols, as I show here. This is a potentiation depreciation protocols, long-term plasticity, this curve here, short-term plasticity, depending on the pulses that you send to the sample. Okay, I think I don't have a lot of time more. Here we have tested a novel 2D perovskite materials through a collaboration with Professor Milic from Finland. They provided us some novel 2D perovskites, and then we integrate them on top of our 3D perovskite, and we observe a better performance. I have to skip this. Also, these 2D perovskites on top of our 3D perovskites help us to have a better lifetime stability compared to the reference devices. Also, we have developed some transistor-based structures using similar perovskite. So we demonstrated in this nice paper synaptic transistors. So transistors that can have synaptic functions. They can behave as memoristic devices. Now in a transistor configuration. And okay, so I think with that, I would like also to thank our group, Professor Gimakis, who's the main PI of the group, our PhD students, and our colleagues in graphene flagship, but also beyond graphene flagship. So with this, I would like to thank you.
Okay, thank you, Kostas, for your very nice presentation. As I mentioned in the beginning, attendees can ask the question using the button at the top of the window. There is a question answer button with a question marks.
Let me find it because I'm in a full screen, so I can stop. Okay.
Just stop sharing and it's fine.
Yes. Okay, I will stop sharing. Questions? No questions up to now.
Okay, so we'll give a few seconds for questions. Meanwhile, maybe I have one question regarding the first part of the photovoltaics. Can you tell more about the manufacturability, perspective, scalability of the production of the solar panels that you presented?
Yes, as I told you, each cell is based on solutions. So in principle, we can print, for this study, we use spin coating for all the cells and the modules, but in principle, you can do this with Dr. Blade or other techniques. So all this technology in principle can be upscalable using even roll-to-roll or other more, or let's say, upscalable printing technologies, but it's fully compatible with a fully printed device.
Okay, thank you. And regarding these neuromorphic applications, devices you presented, they are they are with selectors or without any selectors now, the data you presented?
What do you mean selectors?
Some transistors, for example, or other to build a crossbar array. Sometimes we use selector devices. So do you plan to do this, or you didn't need for your application?
Up to now, we are focusing on single devices. We don't need any selector.
Okay.
But as you correctly say, when you're going to make crossbar arrays, you need a transistor as a selector. But now we are in a process of developing small crossbar arrays, 3x3. And we need a selector transistor, as you know, to avoid streak path, leakage current, and all this stuff. But I think in the next months we will have a mini crossbar array of this kind of membristors.
Okay, thank you. Okay, I don't see any questions. So thank you again for your presentations, Kostas.
Thank you very much for the invitation. Thank you.